Greetings, Astronomy 10, and welcome back to your final lecture video for the semester. Today we're going to be talking about the search for life in the universe. And spoiler alert, we haven't found any except here on Earth yet, but that doesn't mean we're going to stop trying. So, because of the format of this class, it's going to be a little less interactive than I like. Usually there's a lot of class participation during this lecture, lots of questions and voting and debating over definitions and things like that, but there's not going to be any of that, so you're going to kind of have to do all of that on your own. So you're going to want to have a sheet of paper or something off to the side that you can kind of take a tally for your own estimate, for your own guess as to the number of civilizations in the galaxy, in our own galaxy, that we're going to possibly be able to communicate with. Now, let's start at the very, very beginning, and this is where I'd pose my first question to the class, and that, of course, is who believes that we're alone in the universe? And there's always one person, one person sitting in the back or something, say, oh yeah, we're the only man. But that's crazy talk, right? That's geocentric thinking all over again. That would put us in some special place in the universe if we were the only place in the universe where life exists. Is it possible that life only exists on Earth? Yeah, I guess, but the likelihood that there is no other place in the universe that there is intelligent life is so, if you'll pardon the pun, astronomically small, right? Astronomically infinitesimal. That it's geocentric thinking all over again. That would put us at some highly special place in the universe. So much so that, like for us to be that special, that's just astronomically improbable. It's impossible. So it's not likely. I mean, in theory, I guess maybe it's possible, but the universe is huge. Remember, we're talking about a universe that's maybe 100 billion light years in diameter. And that's filled with an innumerable amount of galaxy clusters and superclusters, each of which are made up of innumerable galaxies. And in any given galaxy, if we look at just our own galaxy, you're talking about 100 billion stars right now, to say nothing of, stars that are going to be made and stars that have been and have since gone, and, to think that we're the only life in the universe that's just absurd, right? So if there is life in the universe, because it's incredibly vast, it's got to be out there somewhere, right? How do we find it? It's a problem, right? It's a big question. And so if we're going to try to look for life in the universe, what are we going to look for, even? How are we going to try to find life elsewhere in the universe? And that, of course, begs the question, what is life? It's a big question, right? And if you want to talk about a strict definition as to what life is, this is something that an astronomy class kind of chases its tail around for a little while, because most of us are not, skilled biologists. Most of us are not people that have studied science our entire lives, and so trying to come up with an ironclad definition for what life is no simple task in and of itself, right? It's not easy. So what is life? Well, if you want to kind of look up the dictionary definition as to what life is, the first thing you'll see is that life is the quality that distinguishes you from not being dead. And that's not very helpful, because rocks aren't dead, stars aren't dead, but they're not alive either, right? So what is life? It's not an easy thing to answer, but suffice to say that life as we understand it, you know, there are several basic characteristics. Life reproduces. Things that are alive need to take in energy from the environment in order to sustain themselves, right? All life reproduces, right? It doesn't matter if it's plant life or bacteria or mammals like us or birds or, you know, whatever, reptiles, amphibians, insects. All life reproduces, right? Otherwise it wouldn't be around anymore. Okay, so what is it then that all forms of life have in common? We don't have a single method of reproduction, right, that's the same. Plants, you know, some of them make seeds and some of them, you know, multiply. Bacteria just kind of replicates itself. We don't replicate ourselves, right? So is there some kind of common thread? And at this point, usually somebody says something like DNA or something along those lines. And really, the common thread that all life, at least as we know and understand it, is carbon. Carbon has a very funny property. It has just the right number of electrons in its outermost orbital, such that it can bond 4 times. And the amount of electronegativity that it has, that is how greedy it is to try to steal electrons from other atoms, it's not real strong, it's not real weak, it kind of is really happy sharing, and so it likes to make what we call covalent bonds, right? And as a matter of fact, it's so kind of neutral in this regard that carbon likes to make chains with itself. It's such a predominant feature that if you've ever seen any kind of like diagrams of any organic chemistry or whatever, it's kind of understood that at the vertices where like the lines make corners and stuff like that, that there's a carbon atom there. Because carbon is just so ubiquitous. It's everywhere, right? In anything alive, of course. That carbon makes these nice chains that you know, eventually make amino acids, that make proteins, that make DNA, and so on. Carbon. So basically, all life as we understand it is carbon-based. Right? So, if we want to try to look for carbon-based life in the universe, maybe we'll have kind of a shot. There's an upcoming field of in astronomy we call astrobiology. And one of the aims of astrobiology is to try to employ the knowledge that we've gained so far in physics and biology, chemistry, in order to try to look for some kind of signatures in, say, the spectral signature of a planet or something like that, to see if maybe that there would be life there. We think that if we can see oxygen in the atmosphere of a planet, that probably there's at least some kind of life there, because life as we understand it, plant-based life, things like that, will force an atmosphere to accrue oxygen at 10 times the rate of any kind of geologic process. Stands to reason. And so we could possibly start trying to employ these techniques to look for life in the universe. So far, we haven't found it anywhere in our own solar system. There's no life on Mars, there's no life on Venus, there's no life on Titan, there's no life, you know, on Enceladus or Europa. There's no life anywhere in our solar system except here on Earth. People have speculated that maybe there were microbes on Mars, and some meteorite that came from Mars allegedly might have had some microbe fossils in it or something like that, but there's never been any definitive evidence that that was the case. So long story short, we have not found life anywhere. except here on Earth, the one and only place so far. So, if not in our own solar system, where do we look for life? How about if we wanted to try to communicate with a civilization at the very far edge of the observable universe? How long would it take for us to say hi, and then for them to say hi back? Well, if we're sending like a radio signal or something like that that travels at the speed of light, which again is the ultimate speed limit in the universe, right? It would take 13.7 billion years for the light signal to get all the way to the edge of the universe, and then another 13.7 billion years for a grand total of, what is that, 27.4 billion years. For just a hi and hi back kind of interaction. I don't know about you, but I don't have that kind of time to sit around and wait. What about if we wanted to have a conversation with someone in the Andromeda Galaxy? They're our next largest, nearest neighbor galaxy, right? Maybe that would work. How long would that take? Well, they're 2.5 million light years away. So that means it would take 2 million years, 2.5 million years, excuse me, for a radio signal to get there, and another 2.5 million years to get back. So 5 million years for a hi back. We don't got that kind of time either, right? What about in our own galaxy? Well, if you remember, the Milky Way galaxy is about 50,000 light years in radius. So if you went from the core to the edge, that's 50,000 light years, meaning then the Milky Way galaxy in total is about 100,000 light years from end to end, if we're talking about the disk, of course, not counting the dark matter halo and the globular clusters and whatever, right? Just the disk, just the main population of stars, right? And so if we're going to look for, say, a star that has planets orbiting it that have life on one of those planets that's like us, that's probably where we want to look, right? Now, if we're talking about the farthest distance from here, where we are, just near the outskirts of the suburbs of the Orion Arm, all the way to the far end of the galaxy on the opposite side of the galaxy's central bulge, right? The core. That's about 75,000 light years or so, right? So it would take 75,000 years for a signal to get there, and then another 75,000 years for them to bounce a signal back to us. That's about 150,000 years. Now, as a species, we've been around for about 200,000 years. So maybe it's starting to sound reasonable, right? But how many civilizations should there be in our galaxy? How many star systems are we going to have to sift through and try to send signals to and receive signals from in order to try to find one civilization? And what's the likelihood we'll find one of these in our lifetime? So we're not actually the first people to try to ponder this. Back in the 60s, Dr. Frank Drake proposed an idea, a guess, that would sort of estimate the number of civilizations in the universe and thereby hopefully give us some idea, some guess, some estimate of how likely we would be to try to find life in the universe. In reference to Dr. Frank Drake, we call this the Drake equation, and it was originally contrived for the SETI project, the Search for Extraterrestrial Intelligence, back in 1961. And it looks something like this. Drake equation. Essentially, we're looking for the number of civilizations in our own galaxy that are existing around our time that we can communicate with. Now, essentially, what we want to do is start with the number of stars in our galaxy that could possibly have planets around them, and the number of those planets that could possibly support life, and the number of those possibly life-supporting planets that develop life, and the percentage of those that develop intelligent life, and the percentage of those that eventually form a civilization such that they develop the technology necessary to communicate, right? But stars only live a certain amount of time, right? And so we don't want to just start with the number of stars. We can take a nice shortcut and start by saying we want to look at the rate of star formation, because that takes a few things into account, right? Stars are born and die. Not all of them are around long enough even for planets and life to form. Like if you talk about a class O star that only lives, you know, 1,000,000 years, that's not enough time for life to evolve, right? And so if we compare the total number of stars in our galaxy to the percentage of those that are actually going to be around long enough that they can eventually form life and all those other things, it basically boils down to an analog, that is the rate of star formation. The number of stars that form in our galaxy every Earth year, right? Every year. Okay? So we're going to start with the number of stars that get born every year, essentially. And then, for mathematical reasons that are kind of out of the bounds of the scope and breadth of a class like this, this basically boils down to the same thing. In any case, so let's say we have a number of stars, right? We have a rate of star formation. That's basically how many stars in our galaxy are eligible, right? Okay, so let's say we have a star, okay? What fraction of these stars, what percentage of these stars are going to have planets? Next logical step, okay? And then, if a star has planets, how many planets that are, actually, sorry, I got the wrong subindex here. How many of these planets are going to be Earth-like? That means they're going to have to be capable of supporting life. How many Earth-like planets are going to be per star system that has planets? Okay, it's starting to get complicated already, right? Okay, now assuming that we have a planet that is Earth-like, how many, what percentage of these planets are actually going to develop life? And then, assuming life develops, what percentage of planets, Earth-like planets that develop life, are going to develop intelligent life? Fair question, right? Okay, once we get that, what fraction of these planets that have intelligent life develop on them are going to develop the necessary civilization for communication? And finally, how long are these civilizations going to be around long enough to communicate with us? It's a fair set of questions, right? Now, what I want to do is I'm going to tell you some science facts, right? Some experiments that we've done and things like that in order to try to give you some information to make your own guess as to what these are. Okay? And so what I want you to do is to come up with your own estimate for the Drake equation. And then we'll talk about the consequences of that. How many stars about we should have to try to look at, and so on. Okay, now the first one, I'm not going to tell you anything. You're just gonna kind of have to guess. This one's always really fun. I'm going to tell you essentially what the values that the scientific community at large thinks, what we think is really out there, and then you can compare that to your own, right? So keep a running tally as we go. This is a lot more fun with an interactive class because we have a bunch of people propose a bunch of different numbers and we vote on them to see, you know, what we think, and then we compare that to the scientific estimate. So this is just kind of have to be a guess. We do have some data, but don't worry about it, just guess. Frank Drake's original guess was that there was about 1 star born every Earth year. And the new scientific community estimate is probably closer to about 2.25, with, you know, better scientific data and so on. Long story short, there is star formation happening, but star formation kind of takes a long time, and even though the galaxy is pretty vast, right, there's, you know, something like 100 billion stars in it, and there are stars being made all the time. It takes a long time to make a star. And so in an Earth year, which is only 365.25 days, and even though we've got a population of 100 billion stars or so, we're probably not talking about many more than that. Maybe a couple stars, 1, 2, 3, maybe at the most. Now, most likely, you probably guessed something like 100,000 or 1,000,000, and that's fine. Okay, just leave it. Okay. This next one is the fraction of stars that are going to have planets. And the best guess that we have is, you know, probably close to, I don't know, we can kind of wager a good guess based upon the data that we have. So far, we've found thousands of extrasolar planets, right? Just by looking at observing, what do you call it? Doppler shifts for stars, and then looking for extrasolar planet transits. We found thousands of them. And that's, you know, kind of a crude technique. It's not like we were able to travel to these systems to actually see how many planets there were, right? So once upon a time, Drake thought that the number was something like a half. Like half of the stars should have planets. But nowadays, we think it's probably like all of them. Because, again, we can't be special, right? And pretty much all of the star systems that we've looked at, we've seen lots and lots of this stuff. And it seems typical for our picture of solar system formation and star formation that there should be lots and lots of planets in the universe. Right? Okay. Now, the next one is the number of Earth-like planets that there should be for each star system that has planets. Go ahead and think about it for a second, pause it if you need to, and then make your guess. Frank Drake's original guess is that there should be something like 3 Earth-like planets per solar system that has planets. Nowadays, we think it's probably not so many. 40% of solar systems that have planets are going to have one planet in what we call the life zone. It's in one of the images in today's image bank that there's a region around a star where if a planet is too close, the water will boil. And if it's too far away, the water will freeze. And if it's just in the right region, the planet's water will remain liquid like it does here on Earth. Now, why is that important? Why do we care about having liquid water? Well, it just so happens that we need liquid water to act as a solvent for carbon. Without liquid water, carbon can't free itself from, rocks and sediments and whatever to eventually make chains and amino acids and DNA and proteins and so on, right? So we need liquid water. That's important. And I think Frank Drake's original guess was that, maybe there used to be life on Mars because, maybe there was water there, and maybe there's some on Venus, and we didn't know back then because we didn't have the capacity to look through the atmosphere of Venus quite so well. And so we thought maybe 3 based on our own solar system. But now we think it's probably not so much because we've looked and tried to find tons of Earth-like planets. And of all the planets that we found, we haven't found that many Earth-like planets. Of course, we can't see that many planets. Trying to find planets is not easy. And so we think it's probably more than the number that we've been able to see. Okay, the next one is the fraction or the percentage of these Earth-like planets that will develop life. Now, before I tell you what Frank Drake's original guess was and what we think as a community now, a scientific community, let me tell you about the Miller-Urey experiment. Essentially, a bunch of scientists put together a bunch of the gases that we think were in the primordial atmosphere, what was in the early atmosphere here on Earth. Things like water vapor, but also things like methane and hydrogen. And so they took a bunch of these compounds, right, these gases, about half of the things that were actually in the old atmosphere, and they put it like in a sealed glass system, and they boiled some water so that it would circulate. And so they, in the large chamber where the gases were kind of circulating through, what they did is they put like some electrodes so that electricity would spark across it. And they kind of let it run overnight. And the result, what precipitated out of this was a bunch of organic compounds and amino acids. Basically, half the amino acids that make up life were kind of created, if you will, overnight by having an old atmosphere and, simulated basically like a lightning strike. And so it seems pretty likely that maybe amino acids are bound to happen over the course of time, right? Okay. At this time, this is a good time for you to pause the video and make your guess. Okay. Frank Drake's original guess was that this was about 100% there would be life. And that's kind of what we think nowadays also. Judging by our own fossil record, life has basically restarted here on the surface of the Earth more than once. We had extinction level events like what killed off the dinosaurs, and we started, maybe there was some anaerobic bacteria around or whatever, but, we eventually developed back into sentient life more than one time. And, judging by what happened with the Miller-Urey experiment, it seems eventual that we're going to end up with organic compounds as long as we have water as a solvent. And eventually we're going to make amino acids make DNA, and eventually that makes life. Right? Now there is some speculation as to maybe making some other kinds of life, and perhaps this is a good time to talk about it. Life has evolved the way that we understand it from carbon and amino acids making DNA, right? But suffice to say that carbon only does this because it bonds with itself, and carbon is not the only element that in theory could do this. Silicon is kind of down on the next row, right? On the periodic table, it has the same number of electrons in its outermost orbital, and so we'd think that, in theory, it could also do the same. However, what we've noticed is that silicon doesn't really like to bond with itself in nature so much. It doesn't make chains, and so trying to make DNA or something out of it, it seems pretty dicey. We've never been able to do it. And so, while it's a neat idea, and scientists and also science fiction authors and movie producers or whatever have been theorizing it for a long time now, what silicon-based life might look like. All of the silicon-based life that even shows up in science fiction is basically because we develop some kind of self-sufficient and self-aware artificial intelligence. That's the only reason that it exists. And that's not really life in the same way, is it? I don't know, you can decide that for yourself. Okay, the next fraction here, the next factor, is if we just so happen to have a star that has planets that are Earth-like and develop life. Okay, so life actually develops. What fraction of life is actually going to develop intelligence? This is a good place to pause and make your guess. Okay, so you probably guessed that the chance of intelligent life developing, if there's already life, is probably pretty high. And indeed, Frank Drake and indeed the scientific community at large thinks that it's about 100%. Just judging by the fact that, once upon a time there were dinosaurs, right? Dinosaurs were maybe not as intelligent as we are, but they were still intelligent, right? Maybe about as intelligent as Ninja Mouse. As this guy, right? Ninja Mouse. He's definitely intelligent. And, whether he's more or less intelligent than dinosaurs, I mean, that's maybe debatable, right? But he's definitely, he's responded to me, right? And that's definitely what we would call intelligence. So it seems eventual, since intelligent life has developed more than once just here on Earth, that if life is indeed going to develop, that it should eventually develop intelligence, right? Over the course of time, through mutations and so on, biological life should become more complex. DNA is only going to lengthen, right? DNA is not going to get smaller. Okay. Now, this is where things get interesting. The next one is the fraction of intelligent life having planets that are going to develop a civilization that is advanced enough to communicate using electromagnetic radiation or something like that to try to communicate with us, or so we can communicate with them. That's where things get maybe a little different, right? Let's see. Ninja Mouse. Ninja Mouse. Ninja Mouse. Ninja. Ninja, talk to aliens. Ninja. Go build an antenna. Ninja, go build an antenna. Go talk to aliens. Okay? You need to build a radio telescope so you can listen to them, and you need to build a really, really strong transmitter, okay? Like Doc Brown says, 1.21 gigawatts. Go talk to aliens. It didn't work. I don't know what to tell you. Okay, so while we can agree that Ninja's intelligent, right? What's the likelihood that he's going to be able to build a radio antenna? So there's an important distinction to be made here, right? Intelligence doesn't necessarily correlate to having a civilization that's going to be able to communicate, right? I mean, our civilization appears to be the first in our history here on the Earth that has been able to use radio transmissions, and we only did that like in the 1940s or something, so, you know, 80 years, not that long, right? So, if you want to compare that to the 200,000 years that we've been around as a species, or the 4.5 billion years that the planet has been around, what's the likelihood that a civilization is going to develop with the necessary technology to communicate? This is a good point to pause the video and make your guess. Okay, now Frank Drake's original guess was something like 15%. But nowadays we think eventually, given enough time, given sufficient time, intelligent life should develop the ability to communicate, because we did, right? And human beings are stupid. I mean, look at us. We're killing each other over dead dinosaur juice, right? Letting each other die of diseases and hunger and all like that, you know, just so some people can be rich and live luxurious existences and all this stupid stuff, worshiping the profit motive. Humans are dumb. But even we were able to develop the necessary technology, right? I mean, you're getting this from the internet right now. And if we suck this bad, but we're still able to do it, I don't know. I think probably even Ninja Meows over here would probably be able, given enough time to evolve, to create the necessary technology to communicate with aliens. Right? Okay. So, the final piece of the puzzle is, how long, how many years is a civilization supposed to be around such that it can communicate? 10 years, 80 years, like we have, 100 years, 1,000 years, 10,000 years, 100,000 years, 1,000,000 years? This is a good time to pause the video to make your guess. Okay, Frank Drake literally said 420 years. That was his guess. Nowadays, we think it's something like 304 years. Okay? I'm not trolling you with these numbers. These are actually the numbers. Okay? Now, let us make a couple of very quick calculations here. Let me punch up the calculator. Now, if we multiply all of these numbers together, we're going to get a number, a guess, for the number of civilizations in our galaxy. So first, the Drake number. We got 1 times a half times 3 times 1 times 1 times 0.15 times 420 years. And unless I did this wrong, I got something like 94.5. Why don't we just round it up and say it's a nice even 100? Okay? 10 to the power 2. Now, our current estimate is, I don't know, maybe a little better, maybe a little worse. Let's see, 2.25 times 1 times 0.4 times 1 times 1 times 1 times 304. This is something like 272.384. Let's just call it 272. Most likely, you ended up with a number like a million, or 10 million, or 100 million, or a billion, or something, right? Okay. Now let me try to put this in proper perspective here. If there are 100 billion stars in our galaxy, and there are 100 civilizations that are in the galaxy at any given time that are able to communicate, right? Just a guess. That means we would have to try to look very heavily for a very extended period of time at 1 billion stars in our galaxy. We've been looking at emissions, radio emissions from star systems since, the 60s with the SETI program. And we haven't looked at, a billion star systems yet, right? That would be 1% of the population of the galaxy. But we might get to like a million sometime soon. Now, if this number was not 100, but 100,000, and that's actually the number of civilizations that are out there. If there are 100,000 civilizations in our galaxy, that means we would have to look at a million stars to find one civilization to have a conversation with. And that means probably, if we're playing the odds, right, the average distance from us to them would probably not be that long, but probably not that small either, maybe 1,000 light years or so. Maybe just 100. But even then, it's going to take a long time for us to have a conversation, a back and forth, an exchange, a first contact event. So that may or may not happen in our lifetimes, but who knows? We have been theorizing that we could do a lot of interesting things, like use a quantum engine to try to fold space and time instead of trying to travel through it. And that may allow us to travel at faster than the speed of light. So maybe, because we're not actually traveling, right, we're actually folding space and time, maybe we'll be able to explore some star systems, some far-off star systems, maybe even in our lifetimes. But as it looks right now, it kind of looks like a long shot, doesn't it? In any case, whatever your guess is, whatever the real number is, whatever your guess happened to be, whatever the guess of the scientific community is, whatever Frank Drake's original guess was, everyone's guess is non-zero, right? We all think that there are more civilizations out there than us. And so all we can do is try and hope that maybe we'll find them. Of course, the longer that we're around, the more we try, the better communication methods we develop, the better scientific advancements we make, the greater our chances are going to be. So that also seems like an eventuality. So who knows? But as of yet, we haven't found anything. Except here on Earth. And I don't know about you, but if life here on Earth is all we've got, it's not so bad. Rocky meow. I don't know if you can see her. She's right there inside the castle. But she's eating, so she doesn't want to bother over us. Ninja down here is still content to talk to us. Intelligent life, right, Ninja? In any case, that is our last lecture for the semester. Good luck studying for finals. I hope you have enjoyed this lecture as much as I have giving it. And I'll see you soon.